Hello everybody, my name is Mirjana Spalević. I work at the Institute of Hydrometeorology and Seismology of Montenegro. I'm head of IT department. In the next few minutes, I will talk about data collection method in our institution. I will start with history of institution. The Institute of Hydrometeorology and Seismology, as we know today, has long history, starting from 1947, when it was known under the name of Hydrometeorological Institute. It was founded as a governmental institution, and it was related to hydrological, meteorological, environmental, marine observation, analysis, and monitoring services. 13 years later, the Seismological Observatory was founded in 1960, and its main focus was data collection about seismic activities. Those two institutions were merged in 2012, creating Institute of Hydrometeorology and Seismology. Nowadays, the Institute is operating under the umbrella of Ministry of Ecology, Special Planning and Urbanism. The law of hydrometeorological services and on hydrographic activities define the Institute has a mandate for activities in 5 areas: meteorology, hydrology, ecology, hydrography, and seismology. Mandate for these 5 very important areas includes having a responsibility for observation and measurement of hydrometeorological, hydrological, hydrographic, ecological, agrometeorological, and seismic parameters. Further steps are analysis, processing, and archiving of these data, which leads to production of studies, elaborates years book. In order to preserve the data, IT system has been established within database related to climatology, hydrology, hydrography, seismology. Additionally, one more important activities of Institute is issuing weather forecast and warnings during the emergency situations. Currently, Institute has 110 employees organized in 4 sectors and 3 departments. Sector of meteorology and air quality, sector of hydrology and water quality, sector of hydrography, sector of seismology, and 3 departments: Department of IT system, Department of International Cooperation, and Administrative Services. The sector of meteorology and air quality is charged for establishment of network of meteo station, weather forecast, data analysis, and preparation of reports. In order to get data in any kind of representation from form, we should start from equipment and method of data collection. In case of main meteorological station, equipment is automatic and it's manufactured by Lambrecht company from Germany. Data are recorded at every 10 minutes and using GPRS method transfer to server. Data that are collected automatically are air temperature, humidity, precipitation, pressure, global radiation, wind speed, and wind direction. Data collected is in accordance with the international standards and requirements of World Meteorological Organization. Apart from automatic measurements, data at the main meteorological station are observed by Institute staff observers and stations and sent hourly, that is SYNOP. When you visit our website, you can easily get information about latest measurement and observe data from main meteorological station. We also prepare data for reuse in XML format, SYNOP XML. In case of meteorological precipitation station, data are recorded every 15 minutes and using GPRS method transferred to server at the institute hourly. Measured parameters are air temperature, humidity, and precipitation. Equipment at these stations are OTT Hydromet company from Germany. Data are also available at institute website. Regarding climatological stations, data are recorded at 7 a.m., 2 p.m., 9 p.m. From monthly journal, those data we manually inserted in database. To sum up, we have 9 main meteorological stations, 29 precipitation stations, and automatic, and 10 precipitation stations with observers. Example of data representation from one meteorological station available on our website. You can find numerical values and graphic values of measured parameters, temperature, humidity, and precipitation. This is presentation of climatological products, analysis, years book, all available on our website. This is a graphic explanation of data collection from automatic station. Data are transferred to server using GPRS network and FTP protocol. Data are furthermore imported to climatological database CLIDATA. CLIDATA system is used for archiving of meteorological data, for data quality control, for administration of climatological and observation parameters. CLIDATA is developed by Czech Hydrometeorological Institute and designed for the Oracle database environment. CLIDATA stores metadata of station that includes station coordinates, altitude, address, station type, measurement program, station instruments, and also value of measured parameters. Description of routine data quality control procedures. Quality control is performed on the 3 levels. Observer of institute carry out an evaluation of the measure values. Meteorological technician checks the logical consistency of data from the hard copies before entering them into the database. Quality control procedure using the methods implemented in the CLIDATA database. Data from 6 main meteorological stations, 4 from Institute of Hydrometeorology and Seismology, and 2 stations located at airports are transmitted daily every hour to the International Regional Center in Sofia and Offenbach. Data are also transmitted through the global telecommunication system to the VMO information system. We disseminate data from Nikšić, Bar, Pljevlja, Podgorica, Podgorica, Golubovci, and Tivat. Institute is issuing weather forecast for Montenegro by using weather forecast products of European Center for Medium Range Weather Forecast and European Flood Awareness System. Also, in the case of severe weather condition, announce warning through Meteo Alarm platform. I will mention now briefly other departments, since it's not our primarily focus in this project. The air quality department is monitoring air pollution on the ground layers of atmosphere. We are also analyzing the influence of local and regional emission sources in correlation with meteorological conditions. The basic air quality monitoring networks include 70 stations. Podgorica area is covered by 2 stations for air quality and 1 for precipitation quality. Department is publishing annual reports. In 2019, in Air Quality Department Station Velimlje has been established through European Monitoring and Evaluation Program for the monitoring the transboundary pollution transfer. Department publishing annual reports. Network of hydrological stations are divided on 2 basins, Adriatic Basin and Black Sea Basin. Sector of hydrology and water quality has a network of hydrological stations for surface and underground water monitoring. The network includes 46 stations for monitoring of surface water and 44 stations for monitoring of underground waters. Data from surface stations are received in real time and presented on our website. Data from surface stations are recorded at every 15 minutes and sent via GPRS every hour, and data from underground station are recorded at every 6 hours and sent to server every 24 hours. The data are further stored in the Hydra software and WSKI database. Hydrological stations for monitoring of surface water are using equipment from OTT Hydromet manufacturer from Germany, and hydrological stations for monitoring of underground waters are using equipment for SEBA Hydrometry company, also from Germany. Example of data representation for one hydrological station also available on Institute website. You can see water level and temperature on hydrological station Podgorica Morača. Department of Water Quality. The Laboratory of Water Quality is accredited in 2010 and re-accredited last year. Accreditation body is annually monitoring the work of laboratory, which is in line with the rules of accreditation. The department is publishing annual reports on water quality, also available on our website. Sector of hydrography is in charge of coastal area mapping. This sector is equipped with highly sophisticated instruments for data collection. We have one boat with multi-beam and single-beam echo sounder, sound velocity probe, and related equipment. The paper and electronic navigation charts are available. This sector has 3 mareograph stations at coastal area for measurement of sea level. Data are transferred to server using GSM technology and GPRS method. Sector of seismology is recording parameters on earthquakes and is reporting for the purposes of seismic hazards. The sector has 10 short period and 4 broadband stations with presenting data on our website. Institute is member of the World Meteorological Organization, International Hydrographic Organization, Intergovernmental Panel on Climate Change, UMETNet, and is cooperating member state of ECMWF. We are using at the moment satellite products, but we are not member of UMETSAT. Thank you.
Okay, so hi, it's me again, and again I would like to talk about the past, but this time not about climate model development and the history of climate modeling, but of the history of our former project, the Clim4Vitis Project, that was also mentioned several times in the last talks and yesterday. So the Clim4Vitis Project, like the MONTEVITIS Project, was a Horizon 2020 project. And just to make the long story short, it is pretty similar to MONTEVITIS Project, and the primary focus of this project was grapevine modeling and climate change impact analysis for the European viticulture. So this was basically the research topic of the project, and we had one specific working package 1 in this project that was about the setup, transfer, and application of a commonly usable synchronized database and of a standardized grapevine model family for different European viticultural areas. So it was all about grapevine modeling, and grapevine models are a pretty huge area of models. So for example, for models just simulating the yield or quality, chemical parameters of the grape, phenological modeling models, and also models that even simulate the whole grape wine plant in 3 dimensions. So in the project we decided to use or to focus on one specific kind of grapevine model, and these are phenological models. So first question, what is phenology? And if you ask the great chat GPT, it tells you that phenology is the study of the timing of recurring biological events in plants, such as the timing of flowering, leaf emergence, etc. And that's pretty accurate. And just to give you an idea how this looks like, I have here some pictures of the grapevine plant in different development stages. So we had bud break, leaf development, then development of the flowers, and development of the grape. These developments can be tracked, and we can measure, for example, the date of the year where the changes from one stage to the other occur, and then we can train phenological models to predict the date of the year for a specific plant, in this case grapevine. And the mathematical model is like here. It is pretty simple for a mathematical model, so we basically have here a function of temperature that accumulates over the year until a specific day be had, and on this day this temperature sum overshoots a specific threshold, and if this threshold is overshoot, then the next phenological stage will be entered. And so this is basically the concept of most of the phenological models. And the phenological models basically differ in this temperature function here. And they are pretty simple models where you just have a linear increase of this function after a certain threshold. So the development of the plant starts after a certain temperature value, and the plant cannot develop before or on lower temperatures. Then we have more complex temperature functions with an upper and a heat threshold. So heat threshold means that after at very, very high temperatures, the plant development deteriorates. We also have more smooth representations of these functions. So for example, a sigmoid function or a double sigmoid function, like you see here. So that was just a quick overview of the phenological model to set the scene here. What we wanted to do in the project is we would like to acquire as much as possible data for the whole European continent to simulate with our phenological models and also perform projections. So what we needed at the end are 3 types of data. First, we need to acquire climate observations. Then we need to acquire phenology observations from different vineyards throughout the European continent. We need these 2 types of data to calibrate and validate our models. And then we also need climate projections to make future projections with our phenology models. So now I would like to go step by step through these 3 different types of data and show you the pitfalls or the problems that we saw during the course of the project. So first, the climate observations. Here we have in Europe the advantage that we have a really huge observation network, and by observation I really mean observations like we were shown in the previous talk. So measurements at weather stations for wind speed, temperature, precipitation or radiation, for example. And we have in Europe, we have a pretty dense network from the meteorological services. And in addition, in the project, we were also able to have some direct observations from Luxembourg. Germany has a specific network in the wine region that we could also access, and then we have in Italy and Portugal also specific station networks that were close to the vineyards themselves. However, there are some problems with station observations if you would like to use them for phenology models, and this is that they are pretty inhomogeneous in density. So for example, if you look here in the Iberian Peninsula, we don't have a very dense network, and it can occur sometimes that your climate observation is like 100 kilometers away from the actual vineyard where you would like to perform the phenological simulation. So, and this will make a difference in the quality of the simulations. And also station data have errors, have missing values, and these also need to, and they have different temporal coverage, and this also needs to be taken into account if you would like to use a station network for the whole European continent. So for us, I mean, we are not many scientists involved in the project, so this was just too much work for us. So we decided if we would like to apply the phenology models on the European scale, we rather take gridded observations, because gridded observations, we have the advantage that they basically cover the whole European continent, and they are based on weather observations, so often the observation stations, but other colleagues basically perform the interpolation, and they basically do these things much, much better than we can do. And here you can see one observation data set, temperature observations that we use at a very high spatial resolution. In general, there are a ton of different observations, gridded observations available over the whole globe and the European continent. So there's the EOPS data set at a very high resolution. There are global data sets, ERA, W5, E5. So there are really many, many grid observations available also for regional studies. And what we decided in the project is to use the EOPS dataset, which is for Europe more or less the gold standard for observations, for grid observations. It has a very high resolution, 12 kilometers, and it dates back, I think, to 1960, up to today. However, there are also some problems with the EOPS dataset. One problem is that we have a limited number of variables, at least in the previous versions. We were also only able to use temperature and precipitation values, which can cause a problem if you use more complex grapevine models that also use radiation or wind speed or cloudiness. And the EOPS dataset also has some missing data, especially if you go to the eastern part of Europe. And for example, here you see in purple all the area that were covered with observations over the full time span. And Greece, for example, has so poor observations in the EOPS dataset that we need to exclude EOPS. So to summarize our lessons learned from the climate observations, we saw that station observations are only for localized studies, so we cannot use them really for Europe-wide studies. Gridded observations would be recommended if you would like to apply your phenology model on the whole European scale. However, you have to take into account that the number of variables is limited, and we have still missing observations that we will try to handle then in the MONTEVITIS project. Then let's go to the phenology observations. So these observations are usually done at the vineyards by human computers again. And here we have the advantage that there's a large that in the previous years there were created several major data collections. So for example, the Pan-European phenology database or the Tempo phenology database at INRA that provided around 2,000 stations each, covering the whole European continent. We have then also from the German Weather Service, we have almost 1,000 sites that are only in Germany. Then in UTAD, so the University of Villarreal, Portugal provided some stations or measurements. Unifi, LIST, and the Geisenheim University also provided some observations. The problem, as I try to indicate here with this data, is that some of the data is restricted, and restricted means to scientific usage mainly, or internal usage. This is a problem if you would like to distribute the data to other scientists or commercialize the data. And another problem is that the pre-processing is really, really time consuming because they are in different formats. You have stations that are that appear in different data sets, but in different formats with different values. So you have to take care of this, and this is really, really time consuming. We have to pre-process these data separately, and what we end up with is a station data set with almost 4,000 sites throughout Europe. Here you can see a map where these sites are situated, basically. We have in total almost 350 varieties, different grapevine varieties covered. 123 different varieties covered. However, most of the varieties most of the stations we have acquired do not capture or save the actual variety they use. The only thing they save for most of the station is a early ripening variety, late ripening variety. This is partly data that we cannot really use, and this continues also for the whole data set. So if you look over the whole time span covered and all the data that could be in principle available, we only have a data set that has 99% of missing data. And on average, if you go over all the sites in Europe, on average, each site only covers 7 years of observations. So there's we handle here really, really sparse data that has a lot of unknowns in terms of the variety covered. So lesson learned here, the unification and the combination of all the different data sets is really, really time consuming. So 90% of the time was spent actually of on the pre-processing. And we have here the problem that we cannot easily exchange the data because the underlying data has different terms of use and different licenses that needs to be taken into account. And at the end, we deal with very sparse data. Then climate projections. Here we have the advantage that there are a couple of climate projections or a big ensemble of climate projections available from or that were done under the Cortex framework. These were very, very high resolution simulations, 12.5 kilometer resolution, and in total we have 62 different model simulations that are divided or distributed over 3 different socioeconomic scenarios. The problem with this data set that we had is that this data set only covered temperature and precipitation due to the observations. And so this is a problem if you would like to use the data for more complex grapevine models. And the total volume of the data is quite huge if you would like to simply distribute the data within the project. And if you directly use these data here from Cortex, it is also restricted to the scientific usage, to the science only. However, there's an additional problem which also solves this license issue, and this is the observation that these models has a bias. So if you look at the historical period and compare the model simulations to the observations, they have a systematic deviation from the observations, and here you see just 25 model simulations and as compared to observations. And you can see that there are models which are large-scale overestimation of temperature up to 3 degrees and down to -3 degrees underestimation of temperature. And this poses a problem for phenology models because phenology models are highly sensitive to temperature because we accumulate temperature. So in principle, we would accumulate each day this error. So we need to perform a statistical correction of these data, and this is called bias adjustment. And this worked quite well, and it also solved our license issues because if you bias correct the data, you basically change every bit of the input data, and this, according to our lawyer at PIK, will make this data your own, and you can publish the data under your own license. Okay, so what we also collect, I just would like to briefly show you are this European soil data set. What we did not collect but wanted to collect are management data, and also pest and disease data was not collected in the project. However, pest and disease data nowadays are available on the European scale. However, there are also issues with this data set that needs to be discussed. Okay, so then last thing I would like to show you is how did we exchange the data. So we had 2 types of directions for data exchange. One is between the project partner within the project, and one is for the broader scientific community. And here you have again the volume of the data that we tried to exchange. For the project partner, we had the advantage that we could all access the high performance computing at PLK. So we could simply store the data on our cluster and then also perform simulations. For the scientific community, it is more complicated because of the licensing issues, and we were only able to publish the bias-adjusted climate data, yet not the phenology data due to the licenses issues. So lessons learned from the climate model data is the data exchange is a major concern due to the volume within the project and also due to the license issue. Bias adjustment is necessary. In the Clim4Vitis project, we had insufficient variables for more complex grapevine models. So then I would like to close with some advice for future projects and also for the MONTEVITIS project. So at the end, most data for phenology model can be easily accessed. However, especially phenology data needs additional pre-processing. Imputation is needed, bias adjustment is needed for the climate models. The data exchange should be discussed early on in the project. Or not just the data exchange, but also the data data archiving. And what you always need to take into concern is the data terms of use or license issues of the different data that you acquire and try to distribute within the project. Okay, so thank you. And are there any questions regarding the presentation?
Okay, so welcome back. My colleague Daniel and me will give you some insights in the collection of phenological data for the phenology modeling. So a little agenda, so I will tell you some background information, then the important information about the BBCH scheme that we are using, a little guidelines, and then some words about the MONTEVITIS phenology network. And then Daniel will tell you how the data will be incorporated in the model. So first of all, the phenological development of grapevines is mainly driven by temperature. And then we have to ask us, why is it important to know about the phenological classification of a grapevine cultivar? So it's a very important information for information platforms for disease and pest decision support tools, but it's also very important for the wine grower itself because he or she can time the plant protection and the canopy management, because the grapevine susceptibility to different pathogens is different depending on the growth stage, and also the canopy management can vary. So if I do something in canopy management at one point, it can have another influence on yield or maybe aroma components than if I do it later. Then it's also very important to be able to select the right cultivar for one location, because as an example, if I have a location that has or is risky to have late frost, then I should not select an early bud bursting variety, because then I accumulate the risk. It's also useful for researchers to use it for climate change impact studies and also for climate change adaptation. So the wine grower can select a cultivar depending on their maturity period, so in this case with a later maturity period. We use the BBCH scheme, which was defined in 1995 by Lorenz Eichhorn, I think, and it goes from BBCH 01 to 89, and the BBCH stages are not only available for grapevine but also for other cultures. So here you can see the scheme, how it looks like. So in general we have different macro stages. So macro stage 0 defines the bud development, which you can see in the first line. Then the macro stage 1 is the leaf development, and macro stage 5 is about the inflorescence development. And in general, those both stages are developing in parallel. And then we have the sixth macro stage, which is the flowering of inflorescence, and 7 about the fruit development, and then macro stage 8 is about the ripening of berries. So every code has a definition, and there are 2 special cases where we use like our own definition. So this one is BBCH 75, which is usually defined as berries are pea-sized and are hanging. But the problem about is that it's often not reached in parallel for a lot of cultivars. So that's why we use the definition that 50% of clusters should reach or have passed the horizontal, so that they are going to hang down. And the second special case is BBCH 89. So this is described as the berries are, or clusters are ready for harvesting. And we define it as the date the maturity is reaching or passing the first time 60 degree Oechsle, or around 14 bricks. So that we can be sure that all the varieties are ripened, so that they have passed 60 degree Oechsle. So a little guideline how we do our phenology data collection. So one thing which is very important, that there's a meteo station direct or near the vineyard of observation, so that we can use the daily average temperature for the modeling after. And it's good to go through the vineyard and to do the monitoring around 2 times a week. Best would be 3 times a week, but it's hard, so maybe 2 is a good number. And we define that a new phenological stage is reached once 50% of the organs are showing this stage. And it's often that we can't really precisely fix the date, so we should then estimate as good as possible. So as an example, if we observe on Monday that BBCH 61 is reached, and then we go again to the vineyards on Thursday and we see, okay, now we have BBCH 64, then the most likely date for the BBCH 63, which we didn't see right, was on Wednesday. And then for the maturity control, which is, then when we go to harvest, we select 100 randomly selected berries, so we should do it also once a week. And here it's quite important to select them randomly, so we pick different clusters on different positions in the canopy, so from upper and from lower sides, and then also berries from different positions from the clusters, so from behind, from the right side, from above, so that we have a good estimation about the maturity. So now about our MONTEVITIS phenology network. So it's really nice that we have the 4 wineries participating. And then in Rhemisch in Luxembourg we are observing the phenology. And we find out that we have Franak at 4 locations, so for sure in Montenegro, where we can use the phenological data, so from all 4 wineries. And then the second is Cabernet Sauvignon, what we also have in Luxembourg. So again, we can observe it at 4 locations, which is very good. And also for Chardonnay. And then we have Marcellan, Malvasia, and Muscat Ortonel, also with at least 2 locations, which is also quite nice to see. And then maybe you can answer us the question, because we were discussing about the grapevine varieties here, and I don't know, Kratosia. We just saw that it could be the synonym for Zinfandel. Is it right? Okay, so then we have it also in Remisch, so here we have 3 locations, which is quite nice. And then Daniel will tell you how to incorporate the data in the model.
Yeah, thanks, Christina. Yeah, this is more a proposal how we might use the data. And we are usually using a phenological model, which is temperature sum based. I think yesterday we were talking about that there are new models which are quite fancy and driven by artificial intelligence, and this is more driven by human intelligence. And the idea is that it should also be understood by the farmers. And in fact, this Christoph has shown this approach we are using here. We assume that we have no development under a lower temperature threshold, and then once the temperature increases, the speed of the phenological development increase, and there's a kind of a plateau where the temperature conditions are ideal for fast development, but if it's getting too hot, the speed of the phenologic development is going to decrease again. And we are using this approach. It's a uniphen approach based on daily average temperature after bud burst with those 3 temperature thresholds. And the question is, of course, which might be the ideal threshold temperatures. And we investigated this based on, I don't know how many, it's 11 cultivars which are growing in Remisch, and we had around 8 years of observation. And we were trying different combinations of upper and lower temperature thresholds, and to see which temperature thresholds are fitting best to the observation data. This is based on a normalized standard deviation. I know there are some mathematicians here, don't ask me much more about this, but it's a normalization of the standard deviation. So the lower this value is, the better the model works. And we made this for all cultivars, but also on average of all the 11 cultivars, and we find out that the model works best if we have a lower temperature threshold of 10 degrees and the upper threshold of 20 degrees. And then we interpolated this a bit. I remember in the review process there were some questions about this, but at the end we made it to convince the reviewers. Of course, we have never had daily average temperatures above 30 degrees, at least not in Luxembourg. Maybe it's appearing here. I think the warmest day we had once 28 degrees, which means that we have 40 during the day and 20 during the night. And usually during the night, at least in Luxembourg, the temperatures can be up to middle or end of the 30s, but the night temperatures are very rarely above 20 degrees, which is different here, which I recognized already. So we said, it's kind of, we don't have evidence for this 30 degrees upper threshold, but physiologically it makes sense that there might be a temperature where it's getting too warm for the grape wine for the phenological development. And this has been in collaboration with Helda Fraga, and it's also output of the Clim4Vitis project, and it's published in Agriculture and Forest Meteorology, and we were quite proud that we made it to convince the reviewers that it's acceptable. What you can see here on this table is at the end the result. So we defined a temperature sum for each stage. Now, defined is the wrong word. It was calculated. We have all the BBCH stages from 01 to 89, and the 11 cultivars we were regularly observing. And the starting point for all this is the BBCH, so the bud burst for Riesling. It was just a definition because we needed to have a common starting date. How to read this? If we stay at Riesling, of course, at the BBCH 09, the temperature sum to reach BBCH 09 is 0. But to reach BBCH 11, so one leaf is unfolded, we need a temperature sum, in this case, between 10 and 20 degrees of 7. It means if we have, after the bud burst, one day with 17 degrees, the next day already the BBCH 11 will be reached. Is this clear? So it's simple mathematics for you, I know, but it's yeah. The idea was that it should be understandable also for the wine growers. If we fit other curves, they might fit better, or if we use artificial intelligence, but then at the end it's not clearly understandable for many of the people. But if we have, for example, a cooler period, maybe it's an artificial example, with every day 11 degrees Celsius, then it takes 7 days to reach this state. And what's indicated here by the color, you see the red color cultivars are at this stage later in development, and the green ones are very early. Good example is always the Chardonnay, which Christina mentioned. If we are in a late frost region, it might not be the best idea to plant Chardonnay because it's much earlier. Yeah, much earlier. It depends. It's a temperature sum. It can be 3 weeks earlier or 2 days if it's very warm. For example, Chardonnay for the bud burst is a temperature sum of 16 earlier than Riesling. And what's good, that it's open for any other cultivar, and this is our proposal that we might incorporate those data we are selecting now into the model. Yeah, maybe it's also open to discussion. At the end of the project, we will most likely have 3 years and maybe 4 observation sites for at least some cultivars. And I guess it might be possible to recalibrate the model for those cultivars if we have the 3 years of observation. The more years, the better, of course. And honestly, what I will be curious if the model is working, because this was based on the temperature or the conditions in Rhemisch, if it's also working under your conditions, which, yeah, I don't know if I'm, yeah, for me it's an open question if it's, the approach is going to work also with the observation data from here. Okay, so thank you for your attention. If I have 1 or 2 more minutes, I might just go on the web page, because we were discussing about the platform to be developed. And this is an example of a decision support platform which is existing in Germany. You don't have to understand everything, but you might just click on one of the sites. And it's fitted on a daily basis with the observation climatic data, so the meteo data. And there are models for different diseases. This is, for example, Plasmopara viticola, so downy mildew, but also the phenological model is included. What you can see here, on the left it's the past, and on the right it's based on weather forecast. And in fact here the BBCH stages which are simulated to be reached are shown. And you see we are a bit, yeah, our development is not as far as here, so we are expecting the flowering the next days in our case, so BBCH 61 or 63. And maybe it's just an idea if something comparable might be developed combined with the meteo stations which are existing and the recalibrated model with your cultivars, yeah, might be output of the project. Okay, thank you.